Welcome to this explainer. Today, we're going to dive into the invisible plumbing of 5G networks and explore exactly how engineers balance raw speed with user fairness. It's this fascinating tug-of-war happening inside your phone right now, dictating how fast your data loads when you're, just standing in a crowded room.
Here's our agenda for today. We'll start with the 5G traffic jam, move on to sharing the same frequency, discuss the power allocation dilemma, compare fixed versus fair approaches, and finally cover simulating the network.
Let's kick things off with Section 1, the 5G traffic jam.
To really grasp the brilliance of 5G, we first have to understand the massive connectivity bottleneck we face in our data-hungry world. Older networks use what's called NOMA, which forces users to either take turns or sit in completely separate frequency lanes. But 5G NOMA? It does something radical. It lets multiple users share the exact same frequency space. At the exact same time, it's literally like turning a single-lane highway into a massive overlapping skyway.
Moving right along to Section 2, sharing the same frequency.
So how do multiple users share the exact same space without it just turning into a chaotic mess of digital noise? Well, it starts right at the base station, with a technique called superposition coding, or SC. Imagine a master conductor literally stacking signals of different power levels on top of each other onto the same radio resource. It's kind of like recording a loud, booming voice and a quiet, subtle whisper into a single combined audio track.
Then, the real magic happens at your device. The receiver uses successive interference cancellation. We call it SIC. Your phone takes that combined signal and carefully strips away the louder voice so it can distinctly hear the whisper underneath. It's canceling the interference sequentially, based entirely on those specific assigned power levels.
Which brings up a really crucial point. If decoding the signal relies entirely on power differences, the loud versus the quiet, who actually decides the power ratio? Like, how much power does each user really get when they're sharing the exact same channel?
And that brings us to Section 3, the power allocation dilemma.
This is the core trade-off at the very heart of modern telecommunications. Think about it. You have a stark contrast between users depending on their physical location. User 1 has excellent channel conditions. Maybe they're standing right next to the cell tower. But User 2 has weak conditions. Maybe they're out at the edge of the network or deep inside a thick concrete building. To make NOMA work, the weaker user actually needs more power assigned to their signal just so the receiver can distinguish it. But how do we fairly divide that pie?
Well, engineers can use fixed power ratio allocation, or FPRA. This method assigns predetermined, rigid power chunks. Now, this often favors maximizing the overall throughput of the system, making the whole network look incredibly fast on paper. But there's a massive downside here. It risks completely starving the weaker user of the connection they desperately need. Alternatively, they can go with fair power allocation, FPA. Instead of rigid chunks, this system dynamically adjusts the power ratio based on real-time channel conditions and target data rates. It's continuously balancing the scales so nobody gets left in the digital dark, prioritizing fairness over sheer maximum volume. Let's look at Section 4, fixed versus fair approaches.
Let's see how this actually plays out in real-world data. The results are incredibly compelling. Fair power allocation dynamically adapts to actually outperform the fixed scheme by 14% in total throughput. By being smart, responsive, and dynamic rather than rigid, the entire system actually runs faster and way more efficiently. And here is exactly why the fixed approach can fail so spectacularly. If the power ratio drops too low under a fixed power model, User 2, our weak channel user, completely fails to decode their signal. And when that happens, the whole successive interference cancellation process falls apart. The whisper gets drowned out by the shout, and network performance just degrades.
Finally, we have Section 5, simulating the network. Obviously, to prove these theories before building multi-million-dollar cell towers, engineers rely heavily on complex software simulations. Using environments like MATLAB, they map out highly specific scenarios. For instance, they might create a 1,000-meter cell radius using Rayleigh fading coefficients, which is basically a mathematical way to perfectly simulate how signals bounce and scatter in the real world. They then distribute specific user equipments, let's call them A, B, and C, across two base stations, X and Y, to test these exact power models virtually.
And to optimize that dynamic power allocation across these virtual nodes,
the simulations deploy some seriously advanced algorithms. We're talking mathematical techniques like simulated annealing and hill climbing. Think of these like digital hikers, constantly searching the terrain for the absolute highest peak of network efficiency, even under rapidly changing conditions.
But networks aren't just flat circles, right? To accurately visualize and map these massive, multi-cell networks, engineers use geodesic mathematical structures called the Goldberg polyhedron. It's a convex shape made of hexagons and pentagons, and it provides a brilliant mathematical model for mapping complex 5G cell grids across the three-dimensional space.
Which leaves us with this final thought to take away from this explainer today. As 5G demands grow infinitely more complex, and we move toward these massive multi-cell NOMA networks, will machine learning and AI have to take the wheel for real-time power allocation? It's a fascinating question, and one that is absolutely driving the future of global connectivity. Thanks for joining me, and keep exploring the incredible engineering all around you.